research question. Is there a link between this and that? That's your research question. Is there a link between this and that? And I put link in quotes, and maybe I should put this in quotes, and I should put that in quotes. So, for example, is there a link between vitamin D deficiency, which a lot of the American public is deficient in, by the way, and risk for, let's just say hypothetically, a certain kind of respiratory infection? Is there a link between a vitamin D deficiency and a certain kind of a respiratory infection? That's an example of a research question. Now, in your Stats 1 class, if you had a decent professor, you would have been able to distinguish between two types of links. One type of link is called an association, and the other type of link is called a causation. An association and a causation. In other words, does vitamin D deficiency cause you to be susceptible to a certain kind of respiratory infection? Or are, for whatever reason, the sorts of people that are prone to vitamin D deficiencies, they tend to get these respiratory infections? But there could be other factors that really cause the vitamin D deficiency that also cause them to be more susceptible to the respiratory infection. So in Stats 1, you may have discussed a little bit of the difference between an association and a type of association is a correlation. So you might have discussed the difference between a correlation and a causation, but association is a more general term, so it's really a better term. Association versus causation. So in Stats 1, just like in Stats 2, there are going to be two types of links between this and that, and those are associations and causations. Now, what about the this? This is often called the explanatory variable. But in the case of an experiment, we can call this an independent variable. But only in the case of an experiment. Don't use the term independent variable outside of an experimental study. If it's a purely observational study, it's better to use the term explanatory variable. You can sometimes use the term exposure variable. And you'll sometimes see the term predictor variable. So the this here is what we'd typically call the explanatory or the independent or the exposure or the predictor variable. And this term explanatory variable is probably the safest way to go. Because even in an experimental study, you are perfectly legitimately able to use the term explanatory variable. It's only in an experimental study that you can use the term independent variable, technically. Now, what about the that? So the that is typically called the response variable. But what do you think that could be called in an experimental study? Maybe pause the video and see if you can come up with the answer. And if you said dependent variable, well, you'd be right. And You might also call it an outcome variable. But again, you're pretty safe when that you call the response variable. Even in an experimental study, you can use that term, though in an experimental study, the concept of an independent and a dependent pair of variables, it's a really nice idea that we will talk about probably in Stats 2 in more depth than your professor talked about in Stats 1. Okay, so we have the primary research question. Is there a link between this and that? And we know there are two types of links. The this has certain labels that we typically use. The that has certain type of labels that we typically use. And in Stats 1, every research question had an associated hypothesis test. Now, in high school, you probably learned to believe, or you were led to believe, or you decided to believe that the definition of a hypothesis was an educated guess. And in college, you learned that that was not true because we have two hypotheses in statistics. We have a null hypothesis, and the null hypothesis is symbolized with a capital H and a subscript little zero. And the null hypothesis says there is no link between this and that. Now, I'm going to underline no link. That's the null hypothesis. Always in basic college stats, Stats 1, Stats 2, the null hypothesis is always there is no link between this and that. If you guys are taking, a sophisticated medical statistics course and you're thinking, well, there are non-inferiority trials, how come he's not mentioning this? This is basic college statistics. So the null hypothesis in basic college statistics, even in the second course in college statistics, the null hypothesis is that there's no link between this and that. And then the alternative hypothesis. Now, I don't feel like writing the word hypothesis again, so I'm putting these two little line segments here. These are called ditto marks, and the good thing about ditto marks is I don't have to write the word that's directly above it. That's what this means, that this is alternative hypothesis. And this is symbolized by an H with a subscript 1. And the alternative hypothesis says there is a link between this and that. Now, here's why defining a hypothesis as an educated guess in science is wrong. And if your high school science teacher led you to believe that a correct definition of the term hypothesis is an educated guess, that was misleading and wrong. And the reason is, well, think about it, right? These two hypotheses, the null hypothesis and the alternative hypothesis, obviously they can't both be true. Either there's no link between this and that, or there is a link between this and that. In fact, these are called mutually exclusive hypotheses. And hopefully you learned that phrase, mutually exclusive, in Statistics 1. And two propositions are mutually exclusive means that if one is true, the other must be false. So if the null hypothesis is true, the alternative hypothesis must be false. And if the alternative hypothesis is true, the null hypothesis must be false. So if one of these hypotheses is an educated guess, then the other one is the exact opposite of an educated guess. They can't both be educated guesses, but they are both hypotheses. So this is a little bit of a proof that you cannot define a statistical hypothesis as an educated guess. It is absolutely wrong, although really the word absolutely is redundant. What's the difference between being absolutely wrong and wrong? Wrong is wrong. I've heard people say utterly wrong, but wrong is wrong. If there are degrees of wrongness, then I guess you can use things like absolutely and utterly. Nevertheless, I want to really emphasize this point here, that the fact that these are mutually exclusive hypotheses, and in standard statistics, in standard college level statistics, we have both a null hypothesis and an alternative hypothesis. Please don't tell your children that the definition of a hypothesis is an educated guess. Please don't pass that along. We should really let that really fade away into oblivion. But what really is a hypothesis then? Is there an actual definition of hypothesis? Well, it really is a statement about a population parameter or a relationship between population parameters. And that can get mathematically pretty detailed, or it can be extraordinarily simple. Like, for example, the mean of one population is equal to the mean of another population. That's really simple. That could be a null hypothesis. Or we could say, no, the means are different. That's actually kind of simple. And that could be the alternative hypothesis. But this is a little more simple than this. In other words, we just want to see whether there is a link between this and that. And we have these two mutually exclusive hypotheses. The null hypothesis says there's no link between this and that. The alternative hypothesis says there is a link between this and that. And then what we need to do is we need to make a decision. And sometimes we call the decision the conclusion. And that decision is either to reject the null hypothesis or to fail to reject the null hypothesis. And some people say accept. Some college professors will really take offense to saying, oh, it's okay to say fail to say accept instead of fail to reject. And that really, I teach statistics, but I've been a practicing statistician in the real world besides just teaching it. And in the real world, like I worked in industry, I worked in a pharmaceutical company, no practicing statistician in a meeting in the real world with colleagues will ever say, well, we have failed to reject the null hypothesis because the p-value was greater than 5%. They never say that. They always say accept in the real world. But in school, we do tend to push this idea of failing to reject on our students. And it comes from an idea that you might have encountered in Statistics 1. And this idea is the idea that science is a search for models which explain and predict that which we are capable of measuring. That's what science is, a search for models. I mean, really, if you really want to be truthful, science is a search for funding. But I won't get too into the politics. So science is a search for models which explain and predict that which we are capable of observing. And any scientist will admit, if they're being honest, that a model is never 100% congruent with reality. And so somebody who is a purist, who wants to pass along these ideas embodied in statistical inference in a very theoretically pure way, will say, well, we don't want to use the word accept because that's like saying the model is perfect. I'd rather either reject it or fail to reject it, but I don't want to accept it because I want in my language this idea that a model is never perfect. It's just the best thing we have at this point in time. Like we could have a model that says, the masks, they're not that important. And then we can change our mind and we can say, no, we should all wear masks because we get more information. So models, it's very important to understand that models change with time. As we get more evidence, scientific models change. And a politician might use this term of flip-flopping and saying, oh, well, you said this then, but now you're saying this other thing now. Well, how can it be? And the answer is really simple. The scientist is not flip-flopping. That's a really pejorative, denigrating term that people use. The scientist gets more data. And as the scientist gets more data and gets more studies and evaluates the data and the new studies, the scientists may change their mind. And the models may get refined. It's not flip-flopping. It's getting more knowledge, more data, more models. So I'm probably going to use the term fail to reject in this course. Every once in a while I might say accept, but I'll probably try to stick with this idea of fail to reject. Now, the very last idea that I want to get to you is that we have to admit the fact that in science, whether it's market research or whether it's medicine, you have to admit the fact that scientists can be wrong. Statistical hypothesis tests can be wrong. We make mistakes. So there are two types of errors. Now, if you remember from Stats 1, we have a type 1, this is a Roman numeral 1 error. And a type 1 error is the event of rejecting the null hypothesis when the null hypothesis is true. Now, if you didn't memorize this in your Stats 1 course, because maybe, your professor spent like forever on mean, median, and mode and standard deviation and rushed through hypothesis testing, which is actually the most important part of statistics. And maybe you didn't really get to this idea of what a type 1 error is. Well, you really need it in Stats 2. And you have to have it in your long-term memory, and you have to be able to retrieve it from long-term memory pretty easily. So how do you know whether you've encoded this into your long-term memory and you can retrieve it easily? Well, you don't have to struggle with it. If someone says to you, hey, what's a type 1 error? You got to say, oh, it's rejecting the null when the null is true. Quickly, easily, effortlessly. And a type 2 error is failing to reject the null hypothesis when the alternative hypothesis is true. And the probability of committing a type 1 error is called alpha. Now, this is a Greek letter. Some of my students say, where did you get the 2 from? This is not a 2. This is an alpha. It's the first letter of the Greek alphabet. And the probability of committing a type 2 error is called beta. Now, this isn't a B. You see there's like a little tail here. This is called beta. And beta is the second letter of the Greek alphabet. Now, we owe so much to the ancient Greeks. Mathematics and philosophy and logic and reason. We owe so much to them. So that's why out of homage, we use a lot of Greek letters in mathematical disciplines, you know. So alpha, now typically in the real world, alpha is either set to 5%, which is really the gold standard. Now, we don't use a gold standard in the United States of America anymore. But we still use the term gold standard as if, you know, this is the de facto, maybe that's a better term, de facto or default. Actually, people of this generation are probably more used to the term default. This is the default alpha value. And I should tell you also that the alpha value is called the significance level of the test. Now, this is SIG, significance level. This is not 519. Some of my students say, where did you get the 519 from? This is not a 519. This is just like you'd say LOL for laughing out loud. This is SIG for significance level. And 5% is the gold standard, the de facto significance level that is typically used in the real world, though sometimes alpha is set to 1% if we want a greater burden of evidence to reject the null hypothesis. So sometimes. Beta is typically set to 20% in the real world. For example, in medicine, if you want to get an NIH grant, you want to be able to show that your beta isn't going to be lower than 20%. And you do that by spending enough money to collect enough subjects. So your sample size, I hope you remember that term sample size from Stats 1, so that your sample size is sufficiently large enough so that your beta is no more than 20%. But sometimes we can use 10%. Now, I would doubt that your Stats 1 teacher really talked too much about beta. If you had a good Stats 1 professor, you probably did. But, if you had a professor who focused on like mean, median, and mode and concentrating on like, drawing histograms by hand, like on a piece of paper in 2000. Well, I do this video in 2020. If you had a professor who did that, who had you actually on a piece of paper with like pencils and rulers and stuff making histograms by hand, and they didn't get to hypothesis testing or they rushed through hypothesis testing, well, you're taking Stats 2. So we are going to prepare you for the real world, for actually using statistics. And I can tell you, if you get an actual job working for an actual company, you're not going to be, with your little pencil and a little piece of graph paper making a histogram by hand with a ruler. You're going to use the computer. Or your, quantitative analyst or your market research team will put it in, their report and you'll be reading it, but you're not going to make histograms by hand. We will not be making any histograms or box plots by hand in 2020. We just won't. So, I want to give you two other definitions that are really important for this class. So power is 1 minus beta. And power, and maybe I should say it in a more clear context. We really talk about the power of the statistical hypothesis test, the power of the test. And an even more accurate way to say power is the power of the test to detect the alternative hypothesis. So power is 1 minus beta, and power is the probability of rejecting the null when the alternative is actually true. That's a really good thing, right? Power is, you want power to be high, right? Power is the probability of rejecting the null hypothesis when the null hypothesis really should be rejected. That is when the alternative hypothesis is true. And if beta is equal to 20%, then power, which is 1 minus beta, is 100% minus 20% is 80%. So if you've designed a study and you have spent enough money to collect enough subjects so that your power to detect the alternative hypothesis is 80%, you've done a good job. Well, 80% or more, you've done a good job. And you might actually get funding for your study if you're writing a grant. So the last thing you might say, well, does 1 minus alpha have a name? And it does. We're not going to use it too much, but 1 minus alpha is called the operating characteristic of the test. And we're not going to really talk about that too much, but just like power is 80% if the beta is 20%, the operating characteristic would be 95% if the significance level is 5%. So, there is actually one last thing that I should give you as a little Stats 1 review for Stats 2. The very last thing is this idea of p-value. This is the last concept, p-value. P-value is used, p-value is a statistic. P-value is a statistic, but it's a statistic that's interpreted as a probability. Now, you probably remember this from Stats 1. If you had a good Stats 1 teacher, they may have even emphasized this point, that p-value is actually a statistic, but it's interpreted as a probability. It is not really a probability unless you interpret it that way. And in Stats 1, you may have been exposed to test statistics like z-scores and t-scores, chi-square scores, and your professor probably defined the p-value as the probability of observing a value of the test statistic that is at least as extreme as the one observed, assuming the null hypothesis is true. So you're interpreting that as a probability. And that is accurate. You probably want to put 3 words in there extra to be technically correct. You probably want to say the probability of observing in the future a value of the test statistic that is at least as extreme as the one observed, assuming the null hypothesis is true. If you define p-value that way, and you say in the future, it really is a probability if you say in the future. If you talk about the past, you're wrong. So if you say the probability that the test statistic was, you're wrong. Don't go there, right? So probability deals with future occurrences, and that's really important. But the real question is p-value. How do we use it? I mean, how is p-value used in the real world? Like, what do we do with the p-value? Well, there's a very simple, it's called a decision rule. And you may remember this from Stats 1, and this is the very, very last thing I need to give you for your review of Stats 1. If the p-value is less than or equal to the significance level, remember, this is alpha. This is not a 2, this is an alpha. A-L-P-H-A, alpha. If the p-value is less than or equal to the significance level, then reject the null hypothesis. Otherwise, fail to reject the null hypothesis. So let me review a little bit what we did, because this is a review of the important parts of Stats 1. You know, mean, median, and mode, I expect you know. I expect you know when to use a mean. I expect you know that, you know, when you would use a median over a mean, all that kind of stuff. I don't want to get into that. But let's review what we've actually done. So, what we started with was the basic research question that we're going to approach in a second course in statistics. Is there a link between this and that? The this could be called an explanatory variable, an independent variable if the study is experimental, an exposure variable, or a predictor variable. The that can be called a response variable, but if the study is an actual experimental study, you can call it a dependent variable. Otherwise, call it a response variable or an outcome variable. Now, every research question that we deal with in a college-level statistics course has an associated hypothesis test with a null hypothesis, H sub 0, and an alternative hypothesis, H sub 1. The null hypothesis always says there's no link between this and that. The alternative hypothesis always says that there is a link between this and that. The hypotheses are mutually exclusive, meaning if one is true, the other must be false. Do not ever, ever, ever define a hypothesis as an educated guess to your friends or children or family or loved ones, because as you can see, that's wrong. We learned that there were two types of decisions, also called conclusions. We either reject the null hypothesis or we fail to reject the null hypothesis. And we learned that there are two types of errors that we can make. We could make a type 1 error or a type 2 error. And you guys have to memorize these terms because they are extraordinarily important. Probability of committing a type 1 error is called alpha, also known as the significance level of the test. Probability of committing a type 2 error is called beta. Beta has no other name. It should, but it doesn't. I don't know why. But 1 minus beta is called the power of the test, and power is an important thing. We also learned in the real world that the default significance level is always 5%. That's the gold standard. The default beta is 20%, which would mean the default power is 80%. And, you know, Your Stats 1 teacher may not have talked about that. And the last thing we learned about today was that p-value is a statistic that is interpreted as a probability, and that we have a little rule for interpreting the p-value, and that is if the p-value is less than or equal to the significance level, alpha. This is not a 2, this is an alpha. Then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So this is the end. So this video was meant for my students, but if you're not one of my students and you saw this video and you thought this was a good review for Stats 1 and you didn't think I was too wordy or annoying and you like this video, give me a thumbs up and subscribe to my channel. And I know there's something about a bell that gives you notifications, so do the thing with the bell. And I'd really appreciate it. Oh yeah, and shoot me a comment if there's a video on a topic that you would like, and I'd love it. I'll do it for you.